Is kind of a comprehensive overview of what we looked at and studied during the quadratics chapter. It's called Chapter 6, Review Day 4, and the problem that we're going to look at deals with fireworks. So on Google Classroom, there'll be the link. We'll start with this page. Select the graph that best represents your stress level over the past week. I don't know, I always feel mine is like constantly a lot. I don't know if mine's any of these. Maybe this one right here, constantly a lot. Okay, so here's the problem that we're going to look at. The City of St. Louis Park wants to add a fireworks display as part of the Parktacular celebration this year. The city needs to make sure the citizens are safe. Therefore, they need to know how far away the rockets will hit the ground from where they're shot off. The fireworks company wants to make sure that the rockets explode when the rocket is at the top of its trajectory. They need to know how long it will take for the rocket to reach the top so they can set the timing. Since there are trees and buildings in the city, they need to know how high the rockets go. The fireworks company will use rockets launched from the top of a 160-foot tower. The mechanism will launch the rockets so they are initially rising at 48 feet per second. The rocket will be aimed toward an empty field and shot at an angle of 65 degrees above the horizontal. This is the function that represents the rocket's height over time. So we can see the starting value, the 168, the starting speed, the 48t, and then there's the gravity that minus the 16 feet per second, so minus 16t squared. So this is our equation against starting height, starting velocity, and then the downward acceleration. So does it ask us, draw a sketch of the situation. So the starting height is 160, so I'm going to find the 160. What are these going up by? 25. Ugh, not a great scale, is this? It's 25 divided by 4. Right, each box is going up 6.25. So 150 plus 6.25 plus 6.25. Okay, so it's going to be just below the second box. Okay, so there's the starting height at 160. And we know that it's going to go up and then it's going to go down. We don't know where it's going to land, so here's my sketch. It's going to be launched up and then it's going to go down. That's terrible. I wish there was an undo. Oh, there is an undo. Oh my gosh, it just goes one at a time. Okay, let's try this again. Go up. Oh, that's my line tool. Aha. Go up and then go down. Again, I don't know when it's going to hit the ground, so these are my best estimates. Hits the ground. We need to know how high it goes, and then here's where it starts. The fireworks company will use rockets launched from the top of a 160-foot tower. The mechanism will launch the rockets so they're initially rising at 48 feet per second. Again, here's the equation. Negative 16 has to do with the gravity. Where does the 160, what is that? That's the starting height. The 48 feet per second is the starting velocity.
Hello, Pat. Sorry I had a few problems with my Zoom link. It is now up for those wishing to attend the optional meeting.
The City of St. Louis Park wants to add a fireworks display. Okay. The city needs to make sure the citizens are safe. The fireworks company wants to make sure that rockets explode when they're at the top of its trajectory. They need to know how long it will take for it to reach the top. Okay, so if we're talking about the top of its trajectory, if we take a look at it, that's this point right here. It's where it changes direction, so that's called the vertex. Okay. All right, so if they need to know how long it will take, that's going to be time if we look at our graph. Time is at the bottom and then height. So if this is the vertex, xy is our coordinate. Time is the x value. So the x value of the vertex will be the mathematical term because x is the independent variable of the vertex, which is the highest point in this quadratic. Okay, the city needs to make, repeat. The firework, okay, since there are trees and buildings, they need to know how high the rocket will go. So again, one was time, and one is how high will it go. So that's going to be the y value, which is the range or the dependent variable. So this will be the y value of the vertex. Am I on the right slide here? Yes. Because it's the dependent variable of the vertex. Okay. What is the coordinate of the vertex? Oh, so this is the actual graph. I guess we could have just typed that in and found that as well. So there's the 160. It's going to go up. Okay. What's the coordinate of the vertex? This is hard to read. So what I would do is I would pull up a graph and let's type in the equation. And then we can just use our graphing calculator to figure that out. So I'm pulling up the Desmos. So I'm typing in the function. I wonder if it likes, I don't think it likes the t's. So I'm going to use x. So it's 160 minus, plus 48x minus the 16x squared. So I used x in place of t's. Let's zoom out here. I should really change my scale. Okay, so the x-axis, no, I don't need to change that. The y-axis, let's go from like -10 to how high it goes. We know it went over, well, close to 200. I'll go to like 250. Ah, there we go. Now I can see my graph a little bit better here. I can see the top, and now I can find the vertex. So here at 1.5 seconds, it reaches a height of 196. What is the coordinate? 1.5, 196. We got it by graphing. What's the coordinate of the positive x-intercept? Does it let us? Oh, we could have just used this. Silly me. Okay. All right. What is the coordinate of the positive x-intercept? So that's going to be 5 seconds. Oh, seconds. Oh, so let me do that. All right. So 5. What is the coordinate of the y-intercept? Do it in coordinates. So there's that 5, 0. The y-intercept, again, we said the starting value is 0. At time 0, it was 160 feet tall. Starting height. Okay, so now it says, can you write this equation in factored form? Okay, so factored form, review of that. Here are our factors, and it's going to be the opposite, but we need the a value. Okay. So y equals, do we know the a value? But I know it's going to be x, the opposite of 2 is positive 2, and then the x minus the 5. Okay, but now the a value is negative. Oh, this is when we get to match it. So it's negative, and it's, I don't know, pretty steep. Not much steeper than that. Oh, remember the a value is that number in front, silly me. So if I went back, I could have just said, well, our a value is that number in front of the x squared or the t squared. There's where I got the -16 from. Okay. So now it says, order the steps for converting from factored form to standard form. So we did this on review day 2, where we started with factored form. So this is factored form. So here, we'll put this in first place. And then the next step was to multiply any two together. It looks like this is the next step. They multiplied these two together, which I tended to do the first two. And then they combined like terms. It's this guy. And then they distributed the -16. Oh, I guess they used the box here to multiply those. Okay. And then what did they do? Okay, they distributed the 16 and they got the answer. So this is just putting it in order. So again, they used the box to multiply x plus 2, x minus 5. They got this. They combined like terms. They distributed and multiplied everything by 16. And then they got our equation here. Ooh. Okay. So then it says that the x-intercept is 5, 0. What does it mean in terms of the problem? And that means that's how long it will take for the rocket to land at 5 seconds. You can see why the other x-intercept is negative because the starting height was 160. It shifts our graph so that one intercept will be negative. Okay. So this slide right here is just saying, like, how do we find the vertex? And it's saying, what's the middle of -2 and 5? Okay, so the middle of -2 and 5, if we go back to our graph, is right here at about, it looks like 1.5. Let's check it. If I do 5 minus 2 divided by 2, yep, that's 1.5. So the middle, or the average of -2 and 5 is 1.5, and you can see that that is the vertex of our graph. So 1.5 is between that. All right, and then it says, use the x coordinate you found to the left, right, the 1.5, and either form to find the y coordinate of the vertex. Oh, so this is, okay, we did this before where we plug in. So if I do negative 16 times 1.5 plus 2 times 1.5 minus 5, or if I plug in the 1.5 here, it can give me the y coordinate. So I'm just going to plug into this guy, the 160 plus the 48 times 1.5 minus 16 times 1.5 squared. And 196, and you can see that that's what our vertex was. It was 1.5 was the time it takes to reach 196. Okay, how long will it take for the rocket to reach the top? 1.5 seconds. How high will it go? 196 feet, which we figured out by plugging in. All right, let's write the vertex form. We knew the a value. We know it's negative 16. And we knew that it shifts to the right 1.5, so minus 1.5. And then it goes up 196. So that gives us our vertex form. And now put it in order. So vertex to standard, vertex form, where are you? Here was our vertex form. And the next step, we're going to multiply out the 1.5 times the 1.5. And then we're going to combine like, okay, here's what we get. Then we'll combine like terms. Looks like it's this one. And then we'll multiply everything by 16. Ooh, where does this go? Right here. And then we'll get our answer. Combine like terms and get our answer. Okay. All right, so last step, quadratic formula. So first step, we need 0 on one side, done. Next step, we need a, b, and c. So again, this is just how to use quadratic formula. Next, we plug into quadratic formula. Okay, and then we get our three numbers. Okay, they do it in 2 steps. I would probably just do it in 1. So they get that, they get this, and then we split it up. Okay, before we split it up, we get that, split it up, get our 2 answers. All right, so that's just putting it in order. Check. All right, and that's it. So kind of a comprehensive overview of what we did this unit.